The previous video introduced numerical integration, including a couple of built-in MATLAB functions, trapz and cumtrapz. The topic of this video is a couple of other numerical integration functions available in MATLAB. These functions may appear to work differently than trapz does, but their fundamental approach is actually very similar. The main difference is that trapz accepts data points as inputs, whereas the functions described in this video create the data points themselves. In the previous video, we had two ways to represent a function. It could be represented by a set of data points, or it could be defined by a symbolic mathematical relationship. Both of these representations were treated in a similar way by our numerical analysis techniques. The only real difference between these two cases is that if we're given a functional relationship, we create the data points ourselves, which means we can control the spacing between the data points. The advantage of this is that we could reduce the spacing between the data points to improve the accuracy of the solution. MATLAB has two built-in functions to perform numerical integration for the second case, in which there's a functional relationship. The numerical analysis techniques used by these functions are considerably more sophisticated than the simple trapezoidal rule used by trapz, but their basic approach is the same. The MATLAB functions available to numerically integrate functional relationships belong to a special class of MATLAB functions, which are called function functions. A function function accepts a function as one of its inputs. In this approach, you can create an M file which contains the mathematical function you want to integrate and use that M file as an argument to the integration function. There are two MATLAB functions that perform numerical integration. One of them is quad, which uses an integration scheme called quadrature. The other is quad-L, which performs Lobato quadrature. All you need to know about quadrature for this course is that, like trapz, the approach requires the function to be represented as a set of data points. The use of quad and quad-L is identical, and any differences are insignificant for this course, so I'll only talk about the quad function here. This is the basic syntax for the quad function. In this example, the function to be integrated is in an M file named fun_name. That name, without the .m, is the first argument to the quad function and is placed in single quotes. The second and third arguments are the limits of integration. A is the lower limit of integration and B is the upper limit. Quad returns the integral, which I've assigned to the variable I. Symbolically, this syntax corresponds to the integral of f of x between the limits a and b. The function being integrated, f of x, is evaluated by this M file function. This function must accept arrays of x values as inputs and return an array of corresponding values of f of x. When performing the integration, the quad function first creates an array of x values between a and b using the function specified in fun_name.m and calculates the integral. Quad then creates another set of x values with a smaller spacing and uses those to perform the same integration. The two results are compared, and if the difference between them is above a certain tolerance, the spacing is reduced again and the integral is recalculated. Quad and quad-L will keep reducing the spacing and redoing the integral until the difference between solutions is below some threshold value. Once that happens, they return the result. Next, I'll do a demo to illustrate how the quad function works. As my example, I'll integrate the function x squared plus 1 again. The exact solution to this problem is 1 1/3. I'll create an M file named quad_demo, which contains the function to be integrated. I need to define it as a MATLAB function. I'll return a variable y, and I'll send a variable x to the function. The function needs to be able to accept array inputs and return arrays, so my function is y equals x dot caret squared plus 1, where the array operator is important. I'll save the file and return to the command window. Now I'll use the quad command to integrate my function between 0 and 1. The output variable will be I. I'll assign to that the output of the quad function. The first argument to the quad function is the name of the M file containing the function in single quotes.
The second and third arguments are the lower and upper limits of integration, 0 and 1. The quad function returns a value that's indistinguishable from the exact solution for as many decimal points as I can display.
The functions that are input to the quad and quad-L functions don't have to be in the form of M files. MATLAB also allows what are called anonymous functions. Anonymous functions are specified by this @ symbol. For example, if the function is f equals x squared plus 1, this would be the syntax. The @ symbol tells MATLAB that an anonymous function is being specified. This is followed by the independent variable, in this case x, placed in parentheses. That's followed by a space. After the space, the function itself, x squared plus 1, appears. Notice that array operators are used, so the function will accept an array of x values and return an array of function values. The anonymous function is assigned a variable name. I'm using f as the name of my function. Now the quad or quad-L functions can be used to integrate the anonymous function with this syntax. The name of the function still appears first in the argument list, but no quotes are necessary. As before, the lower and upper limits of integration appear next, so in this example I'm integrating the function between values of x of 0 and 1. The value of the integral is returned as before. I'm using the variable I. Now let's do a demo of this syntax.
At the command window, I'll define an anonymous function named y. It'll be assigned as an anonymous function with the @ sign. After that comes the independent variable x in parentheses, followed by a space. Then comes the function to be evaluated, x dot caret 2 plus 1. Now I can use the syntax quad of f, 0, 1. The result returned is the same as in the previous demo.
That concludes my discussion of numerical integration. In the next chapter, I'll finally talk about what I think is the most important topic in numerical analysis, solution of differential equations. Differential equations define the derivatives of a function. In order to determine the function itself, you need to integrate the derivative. So, in the next chapter, we'll be using concepts from the chapters on numerical differentiation and numerical integration.